Thanks a lot to the organizers. It's promising to be a very exciting conference. It's great to be in Taiwan, and thank you for being here. For those members in the audience. So this is about quantum cryptography. Quantum cryptography is already a very vast subject, so we'll simultaneously try to give an overview as well as go into some of the basic topics that we should know about for those who want to work in this area or that are curious. So what is quantum cryptography? Let's look at what is cryptography to answer that question. And for classical cryptography, there's many types of definitions you could assign to this. Let's start with information processing in the presence of an adversary. So cryptography is often thought about secret communications, and in fact, for the case of quantum cryptography, quantum key distribution is the most successful technology so far, to the point that some people will conflate quantum cryptography and key distribution. Cryptography is much more general, so I wrote information processing, meaning that includes communication, computation, signatures, all sorts of tasks that you would want to do that involve processing information and multiple parties. Or one or multiple parties, and at least one of them being adversarial. So adversarial is that they're trying to eavesdrop, they're trying to change the message, they're trying to find information about the message or compromise the communication, etc. In the quantum case, this will be information processing in the presence of an adversary, just as in the classical case. And then we'll say that at least one party has quantum capabilities. So quantum capabilities could be sending, processing, storing quantum information. And what may not be immediately obvious here is that the party could be the adversary. Maybe the honest parties, Alice and Bob, let's say, are completely classical, and in this case, we'll assume that Eve has access to quantum processing and or quantum memory, etc. So that would also fall under quantum cryptography. And as far as a tutorial talk at QIP on quantum cryptography goes, well, there was one in 2018 in Delft, exactly the same day as today. Wait a minute. Whoa, that's really weird. Okay, exactly the same day, but another year. This was by Kristen Schaffner. The materials are available online. I couldn't find a video. I could find the slides. And this was, 2018 was kind of right following a survey paper that I had co-authored with Kristen Schaffner called Quantum Cryptography Beyond QKD. So that was 2016, where we kind of surveyed what was going on in cryptography other than QKD. Quantum key distribution, we'll talk about it coming up. Very successful. A lot of people know about it. Other than QKD is tons of other areas. And actually, at that, 2016 was a little bit of a turning point where we were going from, we surveyed mostly the information theoretic type of primitives, and starting in 2016 and ongoing, there was huge advances in quantum cryptography beyond quantum key distribution, where we would combine classical cryptography with quantum information, really sophisticated classical cryptographic tools, let's say, to get more and more interesting functionalities. Anyways, I'm getting ahead of myself. What I wanted to do is point you to this tutorial and say how ours may complement it. Ours today may complement it. As part of this tutorial, what Christian did was kind of map the landscape of quantum cryptography at that time. And it's so the center here, quantum crypto, and then there's some main topics. that kind of go around, and some subtopics that are certainly difficult to read from there, but this gives you an idea of the quantity of stuff. At that time, the green bubbles represent areas where there are opportunities to solve interesting open questions. Some of them have been solved by now, some of them are still open. I don't necessarily want to go over all the details. Let me tell you that there is different categories here. There's quantum advantage, where we'll see that there's cryptographic situations where using quantum degrees of freedom enables us to achieve levels of security slash functionalities that don't exist classically, that we really can't conceive of classically. So this includes quantum key distribution, quantum money, device independence. And by the way, like right now, I'm kind of assuming that you maybe know some of these keywords. If you don't know them, don't worry. Then we're going to go into some of the basics coming up. There's quantum data. So here we're interested in, remember this information processing part of quantum cryptography. Well, when we add quantum, it means that the input might be quantum, the circuit might be quantum that we want to compute. So that means that we want to lift what we know in conventional cryptography. For instance, if you're trying to securely compute a two-party functionality, then the quantum version of that would be to securely compute a two-party unitary. So that requires new techniques. And so this quantum data represents this and includes things like secure computation, which is the example that I was just mentioning, and quantum secret sharing, security notions for quantum encryption, quantum message authentication, etc. Over here we have post-quantum cryptography. And as a disclaimer, we're not going to talk about post-quantum cryptography today very much at all. This is an entire area. It's very important right now in light of quantum computers being able to factor and break discrete log cryptographic algorithms. And post-quantum cryptography refers to cryptography that is only requires classical devices. So the parties can encrypt using keys as in conventional cryptography with classical ciphertexts. And that where the power of the adversary is quantum computation. So there are techniques right now, such as lattices and let's leave it at lattices right now, that are candidates for this post-quantum crypto, and it's become super relevant in light of this NIST competition that's going on. Another category is tools. So this is maybe, I like this category. So this is what are, and kind of echoing the tutorial that we had this morning, what's in your toolbox if you're a quantum cryptographic designer? How are you going to put the building blocks together in order to create a cryptographic protocol? And so in a way, this is kind of similar to designing quantum algorithms. You want to know what are the basic ideas. These are usually very mathematical tools. You'll have a theorem, you'll have a proof technique, and then you'll want to apply it to a new adversarial setting or a new functionality. And I would complement Robin's approach, where he had a blue dot, which was the goal, and then the beginning, which was what we know what to do, and then we wanted to increase that towards the blue dot. My most successful work so far has been not reaching the blue dot, but figuring out another dot, a green dot, that I didn't even know existed, and that as I was going along, I realized, oh, that's even cooler. Let's go for the green thing instead. So, yeah. Okay, so what does the landscape look like for 2024? We are 6 years later, and the main categories are still the same. There's been many developments, and just to put out there some buzzwords, certified deletion, proofs of destruction, quantum signature tokens, copy protection, quantum position verification, unclonable encryption. So those are all in quantum advantage. In tools, As I mentioned, something that's been really productive is combining classical assumptions and classical techniques with quantum. Other tools are entropy accumulation, really useful for proving quantum key distribution in some new models, self-testing, monogamy entanglement, post-quantum reductions. Quantum data, a big topic is pseudorandom quantum states and tests of quantumness. And post-quantum crypto, I don't think I'm qualified to discuss that in detail. We can leave that for another tutorial. Today, contrary to the other speakers, I have no idea how far we're going to get. So here's what's on the menu, and we'll see if we manage to get to the end. I don't need to get to the end, by the way. Feel free to interrupt with your questions, and our friends will bring over the mic so that for the benefit of others and of the recording, possibly. Okay, so topics of today. And on the quantum advantage front, quantum money was the first quantum cryptographic result. So I want to start there, both for historical reasons and also pedagogical, because it's really introduced the technique that is really useful everywhere. We're going to talk about quantum key distribution, because this is the foundation, and also because it's the most advanced, both in terms of market and commercially available devices, and also in terms of understanding security definitions, proof techniques, and noise tolerance. So if you understand quantum key distribution, chances are you'll be able to get to the blue or the green dot. Okay, certified deletion. I think that's maybe the last topic. We'll see if we get there. Tools, I'll be mentioning a really nice cool tool called sampling in a quantum population. And I'll also be mentioning another tool called self-testing. And delegated quantum computation down here, which is in terms of quantum data. So this is to take advantage of the remote quantum computing powers of a quantum server while maintaining some privacy. Okay, I combed the program to give you a preview of what types of cryptographic talks you can expect this week. And also as a disclaimer, often cryptography might be lurking in talks that don't advertise so, and maybe even the office don't know that what they're talking about has links to quantum cryptography, so that could maybe be a challenge for you to discover further links. So we have Monday. This session is not called crypto, but it does have a little. It does have a talk on quantum money by Mark Zandri. There's a crypto session Monday afternoon, and here we have things about one-wayness, public key encryption. Okay, 2 talks about quantum public key encryption, and finite size security analysis for quantum key distribution. So that is related to being able to give concrete security parameters for real world applications for QKD. Then we have a second crypto session on Tuesday, and we're going to talk about pseudorandom stuff, quantum pseudorandom scramblers, pseudo-entanglement, public key pseudo-entanglement, elliptic curve cryptography. That would be in the, we'll see if that's post-quantum or not. A mathematical foundation for self-testing, which has to do with device-independent quantum key distribution. There is an invited, there's a short plenary called entanglement theory, which includes applications to quantum cryptography. And there's a session called BH. I think that's maybe for black holes. I'm not totally sure. And then Well, there turns out that there are some really nice links between quantum cryptography and I think it's called cosmology. So there's non-local computation, information theoretic cryptography, position verification, and there's actually 2 talks on position verification, one that links with holography, and then another talk that links black hole radiation and quantum cryptography. So that sounds super exciting. I think we're going to have a great week. What type of community do we have in quantum cryptography? The flagship conference, other than QIP, so QIP, obviously, flagship conference is called QCrypt, and it has a target audience of both theory and experiment in quantum cryptography. It started in 2011, and kind of similar model to QIP. While also incorporating the experimental aspect. And this is a picture from last August, where the conference was in Maryland. Let me advertise QCrypt 2024. It's in Vigo, Spain. Vigo is just north of Portugal, here on the coast. And I'm kind of personally invested in this as I will be the PC chair. And so I'm coordinating a program committee also with Bing Shi, where the tradition is that there's both experimental and theoretical program committee chairs. So as a preview, the deadline will be end of April. Please submit your best work. And as a special, this week only, I thought I would advertise a call for expressions of interest to serve on the program committee. So I think this could be beneficial to expand the horizons of early career researchers if you feel ready to serve on a program committee, and to increase the diversity and the different topics covered in QCrypt. So let me know. We're building the committee right now. Nominations of if your students or postdocs or your colleagues and or personal expressions of interest or questions, please let me know. Oh, and that's a typo. I am talking about 2024, not 2014. Okay, and while I'm on the topic of advertisements, for those who want to learn more about quantum key distribution, this is an excellent opportunity upcoming this summer, a summer school on QKD. Application deadline is at the end of April. And the idea is actually there's been a summer school on QKD every second year held in Waterloo in Canada, and now it's going to alternate with this summer school in Switzerland. So there's going to be a summer school every summer for the people entering the field or who want to learn more. Okay, and I promise we'll get to the talk eventually. I think it's the next slide. Okay, and something new since the last tutorial is that we have 2 fantastic textbooks now that are available for those who want to learn about the field. So there is a textbook on quantum cryptography in itself and only by Ramona Wolf. And there's a textbook on Introduction to Quantum Cryptography. This second textbook includes other topics. So this is just key distribution, and this one includes other topics as well as background on quantum information itself. And both are very recent books. This one is based also on the online course, also available online. There's videos and exercises by Thomas Vidic and Stephanie Wehner. Okay. Any questions before I start on the actual material? Okay, now the starting point is the famous no-cloning theorem, and which says basically quantum states cannot be cloned. The proof of this no-cloning theorem is very elementary. It uses just the linearity of quantum mechanics. If you haven't seen it, it's kind of fun to look up. And this has profound consequences. Actually, the no-cloning theorem was brought up initially in the history of quantum computation as a big obstacle. People were saying, hey, there's this no cloning theorem, therefore we can't copy quantum states, therefore we can't do error correction. So there's always going to be errors in quantum devices, so therefore we can't do quantum computations reliably. The mistake, of course, here is that in order to do error correction, it's not necessary to copy. So repetition code is a very simple code, but there are much more elaborate codes, such as the ones that we saw yesterday in the tutorial, that don't require copying. And we have been able to, of course, get over that barrier of no cloning in error correction. And we've been able to get over the no cloning barrier in many situations. The really nice thing about barriers is that when life gives me lemons, I make lemonade. Okay, so this means that this is also a barrier for the adversary. An adversary also cannot copy quantum information. So basically, a lot of quantum cryptography is taking advantage of that Eve cannot copy, and therefore we can mathematically conclude something about limitations on her ability. Okay, so for instance, the nice parts about the no cloning theorem is that we can get things like quantum money and quantum copy protected software. There's also challenges, nevertheless, things that are probably unexpected, things like quantum rewinding. And this is a situation where it's a fully classical protocol, but because we want to model the adversary as being quantum, and because the adversary, therefore, will be subject to the quantum no cloning principle, there's some classical proof techniques that are not applicable, and that we've had to really build some powerful techniques to get over those barriers. Same thing with quantum oracles. We're not going to talk about these anymore, or today at least, about these topics, but they're super interesting. We will talk about this quantum money. Okay, so for me, quantum information is much more like a physical object. So due to this no cloning thing, it's much more like a piece of a real thing, like an apple, for instance. Maybe I should have used one of the famous Taiwan fruit that I'm discovering this week. So maybe a pineapple for beginners. Okay, so quantum information is much more like a physical thing. You can taste the fruit, but this leaves a mark. Like if you can sample it or get some information about it, but this will be detectable because you've consumed it. You can share the apple, but there's only one item to be shared total, and well, you can't copy it. And that's very different from conventional information, also known as classical information, where of course you can observe the information, and that's not going to change it. You can share that information, you can copy it and broadcast it, and it can be copied. So a bit string versus a piece of fruit, totally different, and that analogy actually goes quite far in trying to understand how you can take advantage of qubits for quantum cryptography. Okay, so the first application is quantum money, and this is a very nice paper, if you're looking for some interesting reading, for historical reasons, and it really has a lot of insight that was very much ahead of its time. It was written around 1968 and published much later. The story is, at least part of the story, is that this author, Stephen Wiesner, was kind of working on these really new ideas and didn't really find the proper audience to disseminate his work. So after the first manuscript had been rejected, he kind of put it away, and it was only published much later. I'll tell you the rest of the story shortly. So the paper starts with mentioning the uncertainty principle. So this is like the Heisenberg uncertainty principle that you may have heard about, and then goes into novel forms of coding. So that's the important part that we want to remember today. And this paper introduced something called conjugate coding. And here's how it goes. So we'll pick a basis. Theta will be a bit, 0 or 1. beta, the theta being equal to 0 corresponds to the computational basis. 1 will be the diagonal basis. And then we'll pick a bit b, either 0 or 1. And then this gives 4 possibilities. And based on each choice, theta and b, we get a different quantum encoding. So these first 2 rows are the computational basis, ket 0, ket 1. Then the last 2 rows are the diagonal basis, ket plus and ket minus. So it's pretty simple. The huge interest is that you have 2 different bases, and they're mutually unbiased. So I'm getting ahead of myself. So here you go. So here, if you have a single copy of one of these states, and suppose that b and theta are chosen uniformly. So suppose you're an adversary maybe, and you get one of these qubits, and you know that it was prepared according to this formula, but you don't know b and theta themselves. So, well, actually, if you do know b and theta, then you could verify the encoding. So you would project, based on theta, if theta is 0, you project 0 versus 1, and if theta is 1, ket plus versus ket minus, and then you could verify that the correct b is measured. And then intuitively, without knowing b and theta, it would be difficult to create 2 quantum states that would both pass this verification. Okay, because if you don't know theta, you could maybe guess it. But then if you guess theta, you may not have the correct one, and then that would induce errors in your measurement, and then errors in what the next person would do if they were going to verify the state. And the Wiesner encoding would be to do the tensor product n times of this single qubit encoding. So you would have a string of n bits for the basis theta, and a string of n bits for the bit b, and you would produce those n qubits, and that would be the quantum banknote. Okay, so this is how Wiesner envisaged the quantum banknote. At that time, it was presented as photons, which are good carriers of quantum information, with their polarization being encoding the quantum bit, and then you'd have all these photons encoded in your quantum device for your quantum money. Of course, already acknowledged at that time in the 1960s, and still true today, is that photons are not really good at storing information. So I don't suggest that you invest into quantum money, because it's known that it will almost instantaneously decohere and become worthless. Still, we can look at this for our purposes, and as you'll see, this idea really is what enabled the following technology, which is quantum key distribution. So the security argument for Wiesner, okay, this is the 1960s, we'll forgive him. It's a very circular argument, but I find it's kind of cute. So we talk about duplication, copies, and copies of copies of copies. And then somehow this leads to a contradiction. I'm not sure exactly what the contradiction is, but it's impossible. So it's impossible to copy the quantum money. But you know, at that time, the word qubit didn't exist. Okay, we really know there's nothing that was related to quantum information. So this is still very insightful, and this is going toward. We didn't have the no cloning theorem either, of course. So this is really pointing towards all these interesting concepts that we know and love today. So here's the security game that we can think about. So there's a an honestly prepared quantum money state. There's an attacker, and the attacker is trying to create, out of a single quantum money state, is trying to create 2 forged bills, quantum money states. And we want that applying the honest verification that they would both accept. So the question in terms of security is to bound the probability that both verifiers accept for any possible attack here. So how does the difficulty of cloning quantum money scale with the number of qubits n? So we would hope that if you have an encoding with more and more qubits, it would become more and more difficult to make this verifier, these two verifiers accept. And okay, so the other speakers were very good at like having these quizzes, so I thought I should at least try for one quiz. Okay, for a single qubit, okay, suppose that there's a single qubit with for this Wiesner encoding, and one possible attack is to guess the basis theta uniformly. So we'll guess computational or Hadamard or diagonal, measure in that basis, and then resend two identical qubits encoded in theta that correspond to this measurement outcome. Okay, so the question is, what's the success probability of this attack? And here are your choices: 1, 1/2, and 5/8. And I'll give you a moment to think about it, and then we'll do a poll. Okay, so what about 1? Okay, no, it doesn't work perfectly. What about 1/2? Okay. And what about 5/8? Okay, so it's about half and half, between 1/2 and 5/8. And the answer is not 1. And 1/2 is pretty close, but we can actually do, it actually does a little bit better. It actually does 5/8. So 1/2 is, well, okay, you'll guess correctly with probability half the actual basis, then it's going to work perfectly. But then in the case that you guessed incorrectly, you still have a little bit of a success probability there, so you still get a quarter because you might be super lucky that the two it's just one qubit right now, that the two verifiers accept, even though you kind of created something random. So the success probability is 5/8. And actually, this is, you can do better. You can achieve probability 3/4, but the 3/4 strategy isn't really easy to explain. And surprisingly enough, this question of how exactly does the difficulty scale when we have the Wiesner quantum money for n qubits, that was answered completely only relatively recently in 2012, and this paper uses techniques of semi-definite programming. And they show that this, even if you repeat in parallel this Wiesner encoding for n qubits, the probability scales exactly like 3/4 to the n. So, so now we know about the security for the Wiesner quantum money. The Wiesner quantum money is something called private key quantum money because the only person who can verify the quantum money is actually the person that created the quantum money to start with, because that person needs to know what is theta and what is b. So that has limited applications. You could think maybe of what we used to use called subway tokens, which is something that you would get, and then you would only be able to spend at the subway location. So that would make sense, but it doesn't necessarily make sense if you wanted to make transactions in large networks or with a multiple number of merchants. So there's something called public key quantum money that solves that problem, and that's quantum money that can be verified by any user. And this public key quantum money, as well as these two other topics. So this is, the first topic here is noise tolerant quantum money. So the other thing is that if there's a little bit of noise in Wiesner's quantum money, then the bank is always going to reject. And that's not very realistic for at least short-term technologies. And there's another topic called quantum money with classical verification, where the spending the money corresponds to actually creating a classical state, a classical string, and that classical string proves that you've spent the money. So all these topics kind of came back within the last 10 to 12 years, and public key quantum money is still very much a topic of research, and we have at least one talk this week about quantum money. Any questions before we go on to the next topic? Okay, so quantum money is about an authenticity token. It's something that you can verify. It doesn't contain any information in itself. So if you like, there's kind of a hierarchy of information. There's like no information, just like that something exists or doesn't exist or is authentic or not. And then a higher level would be data in itself. So is it possible to make data unclonable, information unclonable? And that's what we want to talk about here. And the story starts in 1979. So this is like 10 years after Wiesner's idea. And there's a computer scientist called Gilles Brassard at the University of Montréal, and Charles Bennett, a physicist at IBM. And they actually meet in the ocean off the coast of Puerto Rico and start talking about quantum cryptography. It's a true story. They were both at a conference, and Gilles Brassard was scheduled to talk about his work on conventional classical cryptography, and Charles Bennett was attending the conference. And Charles Bennett was an acquaintance of Stephen Wiesner, and he knew about the manuscript that Stephen Wiesner had put away, and was wanting to share the idea and kind of bring it to the next level. And this pair really was a perfect match because Gilles Brassard was really thinking about security systems and was very receptive to new ideas coming from quantum physics. So this is what became quantum key distribution, which is using the conjugate coding that we see in Stephen Wiesner's quantum money in order to encode information. So what quantum key distribution does is that it enables a level of security called information theoretic security for secret communications. So the current secret communication systems, you may know about something called symmetric key encryption, like the advanced encryption standard. And this is based on a key that has a certain fixed length. And that can be in principle brute forced. What's the complexity of that? Where is he? Is Robin here? Okay, Robin isn't here. Okay, if anybody sees him today, ask him about the complexity of questions, because like that's what he asked us all morning. Okay, we'll see how many people ask him. So what's the complexity of breaking the symmetric key crypto system with a 128-bit secret key? Okay, and the Grover search can help with square root speed up and the Oracle model, what's it called? Anyways, so RSA RSA is what you do in order to start the encryption scheme. So in order to, it's called public key encryption, and this is even worse. So this one is based on the difficulty of factoring, and Shor's algorithm breaks the factoring, or is able to factor efficiently. So this is also insecure if you're looking for information theoretic security. So what we can do for information theoretic security, it's called the one-time pad. And the idea is that the plaintext is X, and the key will be uniform random. That's what this symbol means, bit. So X is also a bit in this case, and the ciphertext is the XOR. This is the sum modulo 2 of the message and of the key. And the idea is that based on the fact that the key is uniform in itself, then the ciphertext is also going to be uniform as long as we only use the key once. So if you reuse the key K in the one-time pad, there are some obvious ways to break the system. And so this gives us the level of security that we want. So for n bits, you'll repeat this n times. The key will be just as long as the message itself. And there are some practicality issues with the one-time pad, which I'll get to shortly. I want to mention that it has been used historically, and actually I was at a talk last week by Bart Pernille, who predicts that the one-time pad is going to come back with the possibility to have large databases of shared keys on USB keys. So the problem with the one-time pad is the key management problem. So suppose that we wanted in this group to all be able to communicate securely, just in case we need to communicate securely in the future. Well, that would require each person to share a shared secret, different shared secret with everybody else. So for a 2-user network, it's not too bad. There's one secret key, and we'll have 28 secret keys with 8 users, and in general, we have a quadratic number of shared secret keys corresponding to all possible pairs in a network of n users. So this is unfortunate in terms of key management, and this is where we can take advantage of quantum communications. So quantum key distribution is going to solve this key distribution problem. And it's called BB84 from the authors, Bennett and Brassard, and the year of publication, 1984. And I have multiple versions of the quantum key distribution protocol to share with you. This is maybe one of the challenges or barriers to starting in quantum cryptography, is that they're depending on the audience, depending on the application, you'll get different versions of a similar concept presented very differently. And the level of rigor, the type of application, the notation, etc., will change. So this talk is not going to be an exception, except I'm going to try to warn you. So a very high level idea of BB84 quantum key distribution, that is the following. So Alice and Bob want to share a key. What Alice does is she generates locally a key, so a uniform key that could be used for the one-time pad. And then she encodes the key in a pineapple. And then she sends that fruit over to Bob. And then Bob removes the outer layer, whatever, and gets the key. Okay. Using our idea that fruit represents a quantum state, she's actually communicated a quantum state. And using the idea that Eve on the line, if Eve wants to learn something about the key, she's got to taste the fruit. And that can be detected. So that's how quantum key distribution, super high level, is going to work, is we're going to use the quantum encodings to detect if Eve has been trying to learn information about the key. Okay, so eavesdropping, and this is also a very confusing terminology in QKD. We'll talk about errors. So errors can be from different sources. They can be from the imperfections of the quantum communication devices. So there's usually nothing we can do about that, except maybe as an engineering or physics problem. And errors can also be here from the eavesdropping. So whatever Eve was trying to do here to learn something about the key is also going to introduce errors. And in general, we don't make any distinction between the different errors, but we want a protocol that's going to be robust against a small level of noise, typically associated with the errors, imperfections of the devices. Yeah. And so then, thanks to the quantum encoding, Alice and Bob will be able to detect that eavesdropping. And actually what they will be able to do is to quantify the eavesdropping. And if the eavesdropping is at a level too high, they will abort. And if the eavesdropping is relatively low, they'll squeeze it out so that it becomes insignificant. And send a random key. Okay. Oh yeah, so what's the link with the one-time pad? Oh, so we started with the one-time pad, and we said that would be a good encryption scheme. It's information theoretically secure. Well, if we solve the key distribution problem, then we'll use that key generated in the one-time pad. So I'm not going to talk any more about the one-time pad. We can focus on establishing a shared secret key. Okay, version 2, slightly more detailed, and now you'll have some math. So yet there's still going to be some assumptions. So here is a picture of what it looks like in slightly more details. Alice chooses a coding basis. So here we'll have these n number of qubits, where n is 10. And she'll choose a bit. So this is perfectly identical to the Wiesner quantum money. The coding basis is the theta. The bit is b here, and we have like 10 times this thing. So we represent these arrows as the polarization of the photons. If you're talking about photons for qubits, this will be a ket 0, ket 1, a ket 0. This will be a plus, and this will be a minus. And she sends these qubits over the insecure channel to Bob. And then Bob chooses a random decoding basis. So Bob doesn't know the encoding basis here. In Wiesner quantum money, Bob is kind of the same person as Alice. And that's how the bank would verify the money, by projecting in the basis theta. So we don't have that luxury here. So what we'll do is we'll choose a random basis. And Bob measures the qubits received in that random basis, and we'll observe a readout. So what happens is that whenever the bases coincide, Alice and Bob happen, this is going to happen with probability half, happen to have used the same basis, then Bob is going to see the same bit here as Alice. And when there are different bases, well, some cases, Bob could see the same bit, or he could see a different bit, actually with probability 50%. So here he gets a different bit. Then there's a next step that uses classical communication, and where Bob is going to reveal to Alice his choice of decoding basis. So this means that they can, via this public discussion, do something that's called sifting, and they will discard all the rounds where their bases disagree. So this kind of brings us back to the original situation in Wiesner, where the bases always agree. And this is called the sifted key. Okay, and in this model, in this picture so far, the sifted key is going to be equal to the bit value here, where we discard the rounds where the bases disagree. Okay, so no big surprises. The interesting part about quantum key distribution is about what happens when there's an adversary. Okay, so this is also a situation that can be very confusing in some cases. So because this needs to be said with a big disclaimer. In this cartoon, we will implement a simple strategy for Eve, where she guesses a basis, just like Bob, measures in that basis. It's called intercept resend attack. So she guesses a basis, and then based on her measurement result, she resends a qubit prepared based on the measurement result that she saw. Okay, so what happens here, so say she had measured in the same basis as Alice, well, she'll see the same bit here, and Bob will also see the same bit in his measurement. When she measures in a different basis than Alice, then she may introduce errors or eavesdropping that can be detected. Because here, Bob's bit is not going to correspond to the bit that Alice sent, namely because she will re-prepare a state, one of these blue horizontal errors states, and then when Bob measures, it could be probably 50%, it'll be a different bit value than what Alice sent. Okay, so after the discussion phase and the sifting, we will have situations, the one circled in green in this specific case, where there's a discrepancy between the bit string that Alice sent and between the one that Bob measured. And that's how we're going to detect, such as in the picture where Bob manages to detect that the fruit was tasted. We're going to detect that there was eavesdropping and or decide to abort if there's too much, or maybe compensate for the eavesdropping in some post-processing. Any questions right now? Yeah, question over there.
Can you give an example of how he would compensate for the eavesdropping? And
Okay, yeah, we're gonna get to that. There's privacy amplification, it's called. So there's one technicality here, is that there's actually a communication here between Bob and Alice when they do this public this discussion phase, and Alice needs to know that she's talking to Bob. And the quantum communication is not going to solve that problem. So we need to start off with something. It's usually called an authenticated channel. QKD will assume the authenticated channel between Alice and Bob exists. And how do we get an authenticated channel? Well, with a shared secret key. We're trying to establish a shared secret key. So actually, quantum key distribution, fortunately, a short shared secret key is sufficient to authenticate a classical channel. So quantum key distribution should be more accurately described as a key expansion, key expansion protocol. Okay, because they need to start with a short shared secret. There are methods where that short shared secret could be started with a using a computational assumption, such as a public key infrastructure, if you've heard about that. And in that case, there are still advantages to the quantum communication. It's called long-term security, meaning that the computational assumption would need to be broken during the protocol in order to compromise the security. And that is useful because it's called either long-term security or everlasting security. And this is useful because it's easier for me today to be confident that a computational assumption cannot be broken than it is for me to say, yeah, I don't believe that during the lifetime of the security requirements for this message, that there won't be an algorithm that will be able to break this computational assumption. Okay, so how do we get from this sifted key, which is the last row that we had here, to a private key? So there are different phases, and we usually kind of have an abstract point of view of what each phase is doing, and then how you actually do each phase. There's different variants based on your needs and the techniques that you're looking at. So there's a step that has to do with estimating the error rate. An error here is going to come from the combination of the faulty devices and of the eavesdropping. And so just as it sounds, they're going to compare and sacrifice half of the key that they have established so far, compute the error rate on that open. They're going to open exactly half, but also choose randomly which part to open and compare. And if the error rate is too high, they abort and they decide that in this case they were not able to obtain a shared secret key. And what threshold is used in practice will depend on the actual primitives that you're going to be using and the choice of parameters. And in principle, 11% is the theoretical maximum. So based on the concepts of error correction that are underlying here. So that means that an Eve can, in principle, always compromise the channel and prevent Alice and Bob from communicating privately. This is not surprising because Eve could always simply cut a wire, block a channel, and there's nothing we can do to prevent that situation. So really the best Alice and Bob can do here is to detect if an Eve is trying to actively compromise their capacity to communicate privately. Then there's something called information reconciliation, also called error correction. And this is going to correct the remaining strings so that they agree in all positions with high probability. So because of the errors, we might estimate the error rate to be about 5%. It means that on the remaining string that hasn't been disclosed so far, there are errors on those strings. So this means that the key that Alice has is different from the key that Bob has. But the error rate is relatively low, and this can be corrected using a series of parity checks. It's called the cascade method, or more generally using error correcting codes. And we'll see shortly an example. Then the final step is called privacy amplification. So what we do is we take all the parameters we've looked at so far, the error rate, the exact codes that we used for error correction, and we put that into a privacy amplification mechanism. And this is going to, abstractly, you can think about it as Alice and Bob applying a random hash function. So it takes an n-bit string to a shorter string that is going to be more private and is going to basically squeeze Eve out so that the remaining key is uniform from Eve's point of view.
I have two questions here. So the first one is, do we really need to sacrifice half of the sifted bits? Can we do with less? So the second question is 11% based on the assumption of one-way communications?
Ooh. Okay, so for the first question, do we really need to sacrifice half? Half seems like an arbitrary constant, so pretty sure you could do like any constant, and then you'll kind of carry through that that number to the end and make sure that your private simplification works with the parameter that you used. Trying to think what's the pros and cons, but I don't know right now. And then the other one is was about the 11%?
Yeah, I thought you could do a bit better.
Oh, thank you. Yeah, so this, I don't know, maybe you can confirm, is it 11% one way? And if you do two-way communication, you can do slightly better, right? Because then you have access to some larger families of interactive error correction and stuff like that, I think.
I don't remember the right numbers.
Yeah, I don't know off the top of my head, but it seems reasonable.
Yeah, could you comment on the Wegman-Carter authentication? Like, is it cheaper than doing one-time pads and compared to resource? So, for example, if I have n parties who want to each have, let's say, secret pairwise, let's say, authentication between them, is it cheaper to do this compared to like OTPs?
Okay, so yes, absolutely. And the reason is that authentication is not the same thing as privacy. So an authenticated channel is a channel where we know that the message has not been tampered with during the communication. And that does not, in what I just said, that does not imply or require privacy. So fortunately, yes. So I don't remember exactly the link. Is it logarithmic? Maybe even shorter. A short key is sufficient to authenticate n-bit. So you do not need n bits of shared secret in order to authenticate n bits. You can get away with a lot less. We're actually going to come back on these with more details shortly. I want to tell you about the security of BB84 quantum key distribution. So this is a big one. You might see informally, oh, okay, QKD is secure because of no cloning. And okay, yeah, if no cloning was false, so if Eve could actually copy quantum information, then there would be an obvious attack. Eve would take all the qubits on the channel, keep them, and keep one for herself, and send the other to Bob. And then when the basis is announced, she'll have the same information as Bob, and we'll be able to get the same key as Bob. So of course we need the no cloning theorem to be true, but it's not sufficient. So you don't actually see in the proof of security of QKD, you don't see the no cloning theorem. You see embodiments of it. So the actual proofs for the security appeared about 15 years after the protocol itself, and there's a zoo of techniques now that can be used to prove quantum cryptography, quantum key distribution, and they're all very interesting and complementary. So there are techniques related to quantum error correcting codes, definite reductions, which reduce general attacks to single qubit attacks. There are entropic uncertainty relations and sampling techniques. So I want to give you a brief overview of the sampling technique approach because I find it kind of interesting and relatively easy to explain. So before getting into the technicalities of the proof, I want to mention a little bit historically what things happened with implementations. So 1989, we had an experimental demonstration, and the proof techniques came out about around the year 2000. And then we can see commercial applications, such as they're kind of proof of principles, but still commercial applications. Bank transfers secured of QKD, then networks. So this is kind of the state of the art where we have multi-point networks for quantum key distribution. There's even satellite-based quantum key distribution, and the current challenges include increasing distance for land-based quantum communications. And there are a number of quantum key distribution commercial products. This is a sample of the companies that work in this area. So one of the reasons why this technology is so successful is that, okay, it's very applicable to secure communications, which is an everyday need. And the other one is that already it's very practically realizable. So it doesn't require quantum computers, requires simple devices. So on Alice's side, she needs to prepare and send single qubits. There's no quantum memory here, and we're talking about random preparation of single qubits, unentangled states. And then on Bob's side, there's no memory either. What he does is that he measures, as soon as he gets a qubit, he'll measure it in his random basis. And the rest is all classical processing. And the other thing is that noise tolerance, or here I said error correction, but that can also be confusing because there's like lots of things that are called error correction. But let's say noise tolerance to imperfections in the device is incorporated in the protocol, and without changing the technology required, these simple devices are sufficient to overcome the effects of noise. And yeah, so it's tolerant against noise. It's not going to always just abort because there's noise, and then that noise ends up being corrected. So we call this noise tolerant single qubit prepare and measure, and this can kind of be considered the gold standard if you're trying to make a quantum crypto protocol that's called practical. Okay, so this could be contrasted with some quantum crypto protocols that require all sorts of complicated encodings, etc. Quantum memory, etc. Recently, quantum key distribution has taken many interesting directions. So there's something called device-independent quantum key distribution, where the situation is that we're not necessarily going to trust the quantum devices. So in what I've described so far, when Alice prepares a qubit, she knows that mathematically she's prepared a qubit, and that's what we use in the proof. Yet this doesn't necessarily have to be true, because the device itself may have been prepared by an adversary. So maybe when you press a button on your quantum device, it doesn't do what you think it does. Maybe it prepares a qubit based on a hard-coded bit string that the manufacturer implanted into the device. So that's problematic because although the communication channel and the physics looks like it's working, it's actually underlying. There's actually a side channel that leaks the key directly to a possibly malicious manufacturer. So device independence gets around that by making less assumptions about how the device is created. However, it makes assumptions about having access to separate devices that can't communicate, that are space-like separated. There's also something called one-sided device independence in quantum key distribution. Where we somewhat relax that space-like separation assumption into something more practical, realizable, and achieve a type of device independence. So we're not going to go into the details, at least of this, at least as it relates to quantum key distribution. I just wanted to put it out there. There's a really nice tutorial talk that's recorded from QCrypt, the quantum cryptography conference that I mentioned from QCrypt 2019 by Rotem, Arnon, Friedman. There's something called continuous variable quantum key distribution, which uses devices that are even easier to build and more realistically model the quantum physics in nature. This requires a whole new paradigm for the model and security proofs. And another area that is included in the QIP tutorial program this week is the finite size effects in quantum key distribution. So if you're actually using this and want to estimate the security level in terms of a number, so that's what's done in current like AES encryption. We say we have 128-bit security, so and then we associate that with a kind of meaning in terms of the difficulty of the adversary in breaking the scheme, and the result that I'll be showing today is asymptotic. So it says, oh, principle, you could always increase the size and you'll reach the security parameter that you're asking for. That doesn't help if you want to build the scheme concretely today. So there's an entire area that looks at these this analysis at a much more fine-grained level. Side channel attacks is also related to device independence. We want to look at these quantum devices, and this is a whole new challenge. It's also a challenge in getting quantum key distribution widely accepted in commercial applications, because there's a whole new level of complexity here, which is the quantum device. And until we really realize or understand all of its capabilities and limitations, it's hard to really know about the full security. Okay, and there's more and more stuff related to QKD that's of interest. So getting into the possibly a security proof for quantum key distribution, or at least a high-level description, I want to tell you about this nice result of Booman and Fair, called Sampling in a Quantum Population and Applications. And this is among these tools. Okay, so it's a general tool, and then you can apply it to different areas. And in fact, in this work, they did apply it to different areas, one of them being quantum key distribution. So as long as you're able to massage your problem into something that looks like this sampling situation, then you can apply their techniques, and that has been done. So after this work came out in 2010, there's really a handful of quantum crypto applications that use the sampling for their security proofs. And that's pretty good, because there's only a handful of crypto applications that appear each year. And there's this other paper that kind of reviews quantum cryptography by Serge Fair, also one of the authors here. And that's I found that one very useful for this presentation. So to present this, I'll give you a third point of view of quantum key distribution, just to set the notation and to go into a little bit more of the technicalities of how we set up a security proof. Because when you think about it, to prove security of any scheme, actually, the challenge is that you have a for all. It says for all adversaries Eve, whatever Eve could do, then you want to conclude security. Oh, we haven't even defined security for Q distribution, so we'll have to define security, and then show that whatever Eve does, that security is met, and that you can't list all possible attacks. So it's really difficult to come up with the approach that's going to cover all your bases. Okay, so this we've seen. This is the prepare and measure BB84 protocol. So Alice will prepare these qubits, send them to Bob, and then Bob does these sequence of steps here that we've already seen also. And that's how they manage to share a secret. In the presence of an adversary, what the adversary could do, well, we want to make no assumptions. So we had that cartoon previously where the adversary is going to do a intercept resend. In general, the adversary could do anything and kind of forward a state row or transform the conjugate coding states they receive, keep some quantum side information, and send something to Bob. And then the first step in all the proofs that I know of will, it's a thought experiment. We'll imagine that instead of doing this prepared measure scheme where Alice prepares and sends the qubits to Bob, we'll imagine instead that a tripartite quantum state is prepared by the adversary Eve, and we'll call it rho ABE. And then this could be in general entangled. And then these are the three registers of that quantum state, A, E, and B. The register A is sent to Alice, B to Bob, and the adversary Eve keeps the register E. And the reason we do this is that this enables us to reason about the security of the QKD protocol based only on this rho ABE. So as long as whatever we manage to do holds for all rho ABE, then we'll have proven security. Why is that? Well, okay. Oh, first of all, what are Alice and Bob going to do given this rho ABE? Because it looks very different from before. So Alice is going to measure each qubit in a random basis theta. And then Bob is going to do the same operation as before. And the point is that Eve could be honest, and the honest situation is that she would actually send maximally entangled states between Alice and Bob. This corresponds to no eavesdropping in the first protocol in the prepared measure situation. And we can see that this works because when you have this EPR pair, a maximally entangled state, when Alice measures in a random basis, it's as if she prepares on the other side one of the conjugate coding states based on the basis that of her choosing. And therefore, it's as if on Bob's side, he had received one of the 4 conjugate coding states. And the claim is that if we can bound the security, which I haven't defined yet, based on this entanglement-based game, then we'll have security in the prepared measure game. And that argument kind of goes through what I just mentioned. And basically, any attack in the prepared measure scheme that Eve would do has an equivalent representation in this entanglement-based game in terms of preparing a different rho ABE. And so from now on, we're going to do this entanglement-based scheme. And in order to define security, I want to talk about, well, what is this shared secret key at the end? And how do we say that Eve has no information about that shared secret key? Because that's what we want, right? We want to be able to know that, to confirm that from Eve's point of view, she doesn't know anything about the shared secret key. Okay, so here's a quantum cryptography, or even cryptography in general, kind of detector of maybe you should be suspicious, similar to what we had earlier today. If you see a paper that says like Eve learns no information, and that's not quantified in any way or shape or form, that's difficult to really handle. It's like you need to be able to know, what does it mean to learn no information? Is it some bound on some entropy? Is it some information theoretic quantity, etc.? So that's what we need to formalize here. And for that, here's a little bit of notation. So I want to tell you about these classical quantum systems, and rho E. Okay, so this is the first one is a quantum system that's randomized. So condition on, this is some notation. So this is some density that matrix that is represents the system E condition on some random variable taking on the value x. So a classical random variable taking on a value little x. And suppose that we furthermore want to encode that value x into the quantum state. So we'll encode it in the classical basis state, ket x or bra x, and tensor product it with that quantum system that's conditioned on the value x equals x. And this is what's called the classical quantum state, because the first register is a classical state, and then conditioned on that value, you'll have a remaining quantum state. So notice that we could trace out the E system, and we would obtain just this mixture. So we have this concept of independence. If we can write rho xe as a tensor product of rho x and rho e, then these two systems are independent in terms of x being a classical and e being quantum. And we'll take mu x to be the completely mixed state. So this is a can also be seen as a completely representing the completely uniform distribution. So for the quantum key distribution, we want keys to be uniform and independent. So it would not be enough to say that, oh, the key that Alice and Bob have established is uniform, because it could be uniform, but Eve could know all of it. So we want it really uniform and independent. So that can be denoted as this. So X will be associated with the key that they end up agreeing on, and E will be the environment. So that's the register that Eve has. So we'll want to be the key to be uniform and independent, so tensor product with the environment. And so the next concept is trace distance. That there's a mathematical definition. Just for our purposes, the operational meaning would be sufficient. And we'll use this notation delta. Delta of two quantum states represents the probability with which the states do not behave identically. So when they're close in trace distance, for all practical purposes, they behave the same way. So this trace distance leaves us a little bit of wiggle room, because the quantum key distribution protocols are never going to reach the perfection of having equality. So we had in the previous slide something about quantum states being uniform and independent. So that's here. And then we'll ask for the trace distance between the actual key obtained. Rho xe will be the classical quantum system representing the key and the environment that Eve has. So we'll want the trace distance between what actually happened and this ideal situation of uniform and independent being small. And this has been shown to be the right or the correct definition for quantum key distribution, actually after much discussion and debate. So this was some nice work that clarified what we should be aiming for the security of quantum key distribution. And it has a property called composability, meaning that you can take that output here, and as long as this is true, then you can use the key for what we do usually, which is the one-time pad, or actually any other application. So going towards a little bit more details of the proof, we actually want to look at a little bit more details of the actual protocol. And maybe it's not super important, the ones related to the error correction, but basically I had mentioned that we're going to do this information reconciliation using error correction codes, and this is how we can actually do it. And the point is that we end up revealing some part of the shared secret key, but n minus k bits will be sufficient, where k is some parameter of the code. And we'll show later how we can compensate for this leakage based for the error correction. So this brings us to the privacy amplification. And I've already mentioned the idea of applying a random hash function. So how is this done in a little bit more detail, and what does that tell us? So actually, in order to apply the privacy amplification, we need to know what parameters to use for the privacy amplification. And this is really the difficult part of quantum key distribution, is to estimate what's called the quantum conditional min entropy that Eve has on the shared secret key so far. So entropy is a measure of uncertainty in a system. You may have heard about something called Shannon entropy that's used in information theory. Min entropy is maybe more cryptographically relevant. It captures how hard it is to guess the value of a random variable. And really, it's like you should guess the most likely event, and that gives you the log of that probability is the min entropy. And the conditional min entropy is just as the min entropy. Sorry, this is a typo. Just as the min entropy, but there's some auxiliary register y. So conditioned on knowing y, what is the min entropy of the distribution. Just to make it more fun, for the quantum key distribution, we'll add quantum to that. So we get the quantum conditional min entropy for a classical quantum state. So that's the negative log of the success probability of predicting a string x using an optimal strategy and having access to the quantum system E. So this is exactly what we want for quantum key distribution. We want to have bound the quantum conditional min entropy to eventually apply privacy amplification, so that the quantum conditional min entropy becomes even smaller. So we've seen this quantum conditional min entropy gives a bound on the uncertainty Eve has on a classical X, and the privacy amplification is going to convert that into a uniform key. So we'll apply a function f, where f is taken from what's called a universal hash function, a family of universal hash functions, and it has the property that if x is different from x prime, then the probability given the s, so s is a random seed, the probability that the function applied on the random seed on x is equal to the same function with the same random seed applied to x prime should be less than 1 over the size of the k. And the privacy amplification theorem, so you could use, for instance, Renner and Koenig. So this is where you could, in your actual implementation of QKD, you can choose different privacy amplification methodologies. The one here of Renner and Koenig gives you this specific bound, and so this is the bound on the trace distance. This is exactly what we wanted to bound for the security of quantum key distribution. So basically, once you have an estimate on the quantum conditional min entropy being L, and you apply this privacy amplification with these parameters, then up to some exponentially small error, you'll have a secure scheme based on the definition that we had. And the next step is going to be to bound this conditional quantum min entropy, okay, because we've assumed that we have a bound in applying the privacy amplification. And that's where we use the sampling technique. So should I have a few minutes on the sampling technique. I would prefer to finish that. We started a few minutes late. So, okay. So, the sampling technique is inspired by classical sampling, and classical sampling is really intuitively easy to grasp. So suppose you have a bit string and you want to estimate its Hamming weight, and you only have access to reading half of the bits of that string. How could you estimate the Hamming weight? Well, you'll randomly read half of those bits of the string, and you will extrapolate that the Hamming weight should be, the Hamming weight is the number of ones in that string. The Hamming weight should be approximately double the Hamming weight that you've measured by opening the half of the string so far. So sampling is exactly that. And it's applied to, in this case, what we call the relative Hamming weight, which is the weight divided by m. So it's the that way we can give a value for specific bits. That strategy that I just described is called a sample and estimate strategy. And so if you choose a random subset of size linear in m, so here we have m bits, and the subset will be called t, and you output the weight of the relative Hamming weight of the subset of the bits that you've opened, so the white ones, as the estimate of the weight of the entire string. And as long as your sampling is fair, then this gives a pretty good estimate. Actually, for this strategy, using some basic probability bounds, we can bound the error of this estimate. So you're just how far you are from the actual Hamming weight based on the sampling. So the quantum version of this sampling is not obvious to even define or analyze, but that's what Booman and Fair managed to do. And the link to quantum key distribution is coming up. So say you had n qubits, and you wanted to somehow estimate the relative Hamming weight of the quantum string. Okay, well, first of all, it's really not clear what it means, Hamming weight of a quantum system, relative Hamming weight of a quantum system. They do have a nice interpretation, and Booman and Fair, for now, you can think about, well, it could be maybe you have superposition of strings, and you could maybe want to be estimating the relative Hamming weight of that superposition. And it turns out that Booman and Fair are able to relate the error in the estimation in the classical sampling with the error in the estimation for the quantum sampling, and to be close to each other. So the estimate that you would get if you were sampling a classical string is relatively close to the estimate that you would get. You can apply that same estimate to the quantum system. How is this related to quantum key distribution? Well, when Alice and Bob are comparing, and they're doing, just before they do the sifting, they do this discussion phase. And there's a way to turn that discussion phase into a sampling situation, because when you think about it, they're trying to see in how many positions do their strings differ. So that differing could be compared to estimating the Hamming weight, if you consider that the all zero string would be the perfect situations where the strings are equal. So with just a few steps, you can get from the quantum key distribution situation to a sampling game and apply their sampling tool. And that means that we can based on the Booman Fair sampling tool, we can look at the classical sampling problem, which in itself is relatively easy to analyze. And from that estimate, and therefore from the classical sampling, and if you go 2 steps, you can get some little error parameters each time. They just add up. And then that will give us a bound on the quantum conditional min entropy. And if you remember, that's exactly what we needed to know. We needed that bound in order to be able to apply privacy amplification. So there's another thing, is that in the error correction, remember that we had revealed the syndrome related to some error correcting code, and that will reveal information about the shared secret key. It turns out that for each bit that Alice and Bob reveal, that's going to cost you at most 1 bit of quantum conditional min entropy. So we'll take that into account, and then this is what I meant by saying that we need to apply privacy amplification with the correct parameters. So we've estimated all these parameters, and we put them into the formula for privacy amplification that we've already seen, and that's going to complete the proof in order to get that security definition that we had for quantum key distribution. So that's a bit of a mouthful. I want to give you an overview and going into at least the details of at least one approach for quantum key distribution. And the reason, as I mentioned, is that often if you understand key distribution, then you'll be able to apply that to the crypto protocol that you're looking at. In fact, often it's the case that if you understand the adversarial model, okay, so who's honest, who's cheating, do we trust the devices, etc., then it's a question of using the tools that are applicable for that specific adversarial model. So in this quantum key distribution model, we have honest sender, honest recipient, and cheating Eve. If you have a dishonest recipient, then maybe you should look at one-side device-independent QKD, etc., etc. So are there any questions?
I have a question actually. Does any of this require the IID assumption?
Oh, okay, so thanks for the question. Does any of this require the IID assumption? Historically, we did have security proofs initially where they're very difficult to come by. So if it's difficult to come by a proof, let's make an assumption on the adversary. So let's not prove security for all adversaries. Maybe let's prove security for a class of adversaries. So we see this, for instance, in classical cryptography will prove security against honest but curious adversaries. So IID adversary, for the benefit of the people in the room, is that the adversary is attacking each qubit with the same process. And we did have initially security proofs for that. And no, so the sampling does not require IID. If you wanted to go from IID to general, then you could use the definity reductions, but that's not the direction, that's not the path that this is taking.
Hey, I just wanted to ask you a clarification question on the definition of Hamming distance. So I was just wondering, like, is it the same as the Hamming distance for quantum error correction, or different?
Yeah, I would say so. Hamming distance is okay. So we talked about Hamming weight actually in this one. I don't think we had distance formally. Hamming weight is the number of ones in a binary string. Hamming distance will be the number of ones in the difference between the binary strings.
All right, gotcha. Thank you.